Hi, welcome back to es346 Basic Thermodynamics. This is module 8.3 on second law efficiency. The sections in the textbook are 8.2 to 8.3. Here are the two learning outcomes. At the end, you will understand the definition of the second law efficiency, and you will be able to calculate the second law efficiency for an irreversible process. So I want to talk about the second law efficiency. So consider we have a heat engine operating between two temperature. I have a temperature source at 1000, temperature sink at 200 that is generating some work. We could determine what the maximum efficiency is, which would be the reversible efficiency there, and that would be the Carnot efficiency. And any other heat engine that was operating between those temperatures, we know is going to have a lower efficiency. So that would be a real heat engine there, my reversible one. And so we know that our efficiency eta is going to be something less than eta Carnot. And we can calculate eta Carnot. In fact, we can do it with these temperatures we have here. That's going to be 1 minus TL over TH, 1 minus 200 over 1000, or 0.8. And so there our Carnot efficiency is 80%. But if we didn't know what our Carnot efficiency was, and someone said, oh, your efficiency is 0.3, if you didn't know what the Carnot efficiency was, that 0.3 wouldn't mean much, because maybe the Carnot efficiency was 0.3, which means we've got a perfect heat engine. But if it's 0.8, then we're actually not doing all that well. So it would be nice if we had an efficiency that we could go ahead and kind of constrain by the Carnot efficiency. And so if instead we go ahead and define a second law efficiency as our efficiency normalized by the Carnot efficiency, this second law efficiency is therefore going to be between 0 and 1. And now, if we told we only had a 30% second law efficiency with the process, we know we're not doing very good, because we can get that to 1. So that's why this tends to be somewhat useful. So I'm going to come back to this problem here. I'm going to put some numbers on it. Let's imagine that I had 100 kilojoules coming out. If it's 80% efficient, 80 is being generated by work, and 20 is going down here. Now, if my real heat engine was also getting 100 units, and say it was only doing 60, we would go ahead and be doing 40 down there. And if I wanted to calculate the second law efficiency for this, well, we would then have the 0.6, which is the efficiency of my heat engine, over the Carnot efficiency of 0.8, or 0.75. So now we say the second law efficiency of this device is 75%. Now, there's some kind of interesting things. Let me go ahead and draw those heat engines back up here again to put those numbers on it. They were both getting 100. This one was generating 8 units of 80 of work. Our real one was doing 60. This was dumping 40, and this one was dumping 20. Now, if we were to calculate the entropy being generated with this heat engine here, which we know is going to be positive, this one over here generates no entropy, we can calculate what delta S is. And delta S is going to be, well, it's removing 100 kilojoules from a source at 1000, and it is putting 40 in to a sink that is at 200, and so that is minus 0.1 plus 0.2, and that becomes a positive 0.1. All right. So if I calculate what my exergy destroyed is, or delta X, recall that that was T naught S gen. And this right over here is the entropy that I'm generating. So if I was to go ahead and put that in, I've got 200 is T naught. That would be my low temperature times my 0.1. That is equal to 20. So it says that I destroyed 20 units, for example, 20 kilojoules in this process. And if I want to know what my second law efficiency is, I could also say this is going to be 1 minus 20, which is the amount that I destroyed, over the amount that I could have gotten, which was 80, right there, and that number is also 0.75. So there's kind of two ways to go at getting this second law efficiency. Let's go back to this problem we did in the previous module and go ahead and calculate what its second law efficiency is. So just to remind you of the problem, we had this rigid tank of water with this quality and this pressure. We were adding 500 kilojoules of energy to it. And what I want to know is, what is the second law efficiency of storing this 500 kilojoules of energy in this box here as thermal energy? So let's go ahead and calculate what is exergy destroyed in this process. And we know that that is 2 naught Sgen. So how much entropy did we generate? Well, let's calculate our initial entropy. That's going to be SF plus X SFG. We did this in the previous module. We found out that was 4.341 kilojoules per kilogram Kelvin. And then we can go ahead and calculate what S2 was, and that was at the final conditions. And we also did that in the previous module. We saw that that was 4.575 kilojoules per kilogram Kelvin. So now we can go ahead and calculate our exergy destroyed. And that's going to be, we have 5 kilograms, so it's like 5 kilograms. And T naught is 298 Kelvin. And my change in entropy, so 4.575 minus 4.341. And that right there is equal to 350 kilojoules, which is what we were able to calculate before. And so our second law efficiency now, in this case, will be 1 minus the amount that we destroyed, which is 350, over the amount that we could have gotten, 500. And that right there is 0.3 or 30%. So what this means is 30% means that if I was to have 500 kilojoules of energy, say I had a wind turbine that was generating some energy, I didn't know where to store it, so I decided to store it in this water, I'm only storing it with 30% efficiency. And if later on I wanted to get that power back, I can't get 500. I can only get 30% of that 500 back out to go ahead and do some other process. So this storage ability, storing it as thermal energy, clearly is not all that efficient.